Welcome to today's session. In this video, we'll be diving into an interesting problem titled Leftmost column with at least a 1. We'll explore its requirements, discuss different approaches, and work through its solution step by step. Stay tuned to sharpen your problem-solving skills. In this problem, you are working with a binary matrix. A key property of this matrix is that each row is sorted in non-decreasing order, meaning that all the zeros in a row come before any ones. Your task is to identify the leftmost column that contains at least one 1. If no such column exists, you'll return -1. To interact with the binary matrix, you are provided with an API interface called binary matrix. This interface includes two methods, binarymatrix.get x, y, which retrieves the value at a specific position in the matrix, and binarymatrix.dimensions, which provides the dimensions of the matrix as a list of two integers representing the number of rows and columns. To solve this problem effectively, you need to minimize the number of calls to the get method while ensuring that you only access valid indices in the matrix. The goal is to determine the leftmost column with a 1 efficiently, leveraging the sorted nature of the rows to your advantage. The output for this problem is an integer that represents the index of the leftmost column containing at least one 1. If no column has a 1, you should return -1. Let's look at some examples to clarify. In the first example, the binary matrix is represented as 2 rows and 2 columns, 0, 0 in the first row and 1, 1 in the second row. Since the leftmost column with at least one 1 is column index 0, the output is 0. Now consider another example where the binary matrix is again 2 rows and 2 columns, 0, 0 in the first row and 0, 1 in the second row. Here, the leftmost column with a 1 is column index 1, so the output is 1. Continuing with the examples, let's look at a matrix where no column contains a 1. This matrix also has 2 rows and 2 columns, with both rows being 0, 0. Since there isn't a single 1 in the entire matrix, the output is -1. As you can see, the problem requires careful handling of edge cases, particularly when number 1 exists. Additionally, the constraints specify that the binary matrix dimensions will always fall between 1 and 100 for both rows and columns. This means you can encounter matrices of various sizes but should always respect the property that the rows are sorted in non-decreasing order. Minimizing the number of calls to the get method is a crucial part of solving this problem efficiently. Let's consider some specific edge cases you need to handle. First, if the matrix contains all zeros, your function should return -1 because no column contains a 1. Second, in a matrix with multiple rows but number 1's present, you must ensure that your solution avoids making unnecessary calls while confirming that number 1 exists. Third, in a matrix where every element is 1, your function should return index 0 because the leftmost column will always contain at least one 1. Lastly, if the matrix is reduced to a single row or a single column, you must handle it appropriately, as the structure of the matrix changes but the logic remains the same. By addressing these edge cases systematically, you can ensure your solution is robust and efficient. To start, let's consider the brute force approach, also known as the row-by-row search. The idea here is straightforward. Since each row in the matrix is sorted, the leftmost occurrence of a 1 in any row directly impacts the leftmost column containing a 1 in the entire matrix. The steps are simple. We iterate through each row one by one, checking every column in the row to find the first one. As we progress, we track the smallest column index where a 1 appears across all rows. While this method works, it's not efficient for larger matrices. The time complexity is O(m*n), where m is the number of rows and n is the number of columns, since we may need to examine every cell in the matrix in the worst case. Additionally, this approach ignores the sorted property of rows, which could help us save time. As a result, the brute force method, though easy to understand, is not ideal for this problem. A more efficient alternative is the binary search approach, which builds on the fact that rows are sorted. Instead of searching each row linearly, we use binary search to find the first occurrence of a 1 in each row. This reduces the search time for each row from O(n) to O log n. The process involves performing binary search on every row, then updating the smallest column index based on the results. Finally, we return the smallest column index found, or -1 if number 1 is present in the matrix. This approach improves the time complexity to O(m*log n, which is a significant improvement over brute force for larger matrices. However, a key limitation is that this method processes each row independently and doesn't take full advantage of overlaps or relationships between rows. It's a step forward, but there's still room for optimization. The optimized approach, which starts at the top right corner of the matrix, fully leverages the sorted structure of the rows and columns. The key insight is that starting at the top right corner allows us to systematically eliminate rows or columns in a single pass. Here's how it works. We begin at the top right cell of the matrix. If the current cell contains a 0, we move down to the next row since all cells in the current row to the left will also be 0. If the cell contains a 1, we move left to explore earlier columns, updating the leftmost column index as we go. This traversal continues until we either move out of bounds or finish examining all relevant rows and columns. The time complexity of this approach is O(m plus n), making it highly efficient even for large matrices. Unlike previous methods, it avoids unnecessary checks and ensures no cell is revisited. While the logic may feel less intuitive initially, this approach is both elegant and powerful. The top right corner start approach is the chosen strategy because it achieves the optimal time complexity of O(m plus n). This method effectively exploits the sorted structure of the rows, ensuring that we minimize redundant computations. There are a few key observations that make this approach so efficient. First, since rows are sorted, once we find a 1 in any row, all columns to the right of that position will also contain 1s. Second, the movement pattern, left for 1 and down for 0, ensures that we systematically eliminate rows or columns without revisiting any cell. The aha moment in this strategy comes from recognizing that starting at the top right corner allows us to explore the matrix in a way that balances both completeness and efficiency. When comparing the trade-offs, brute force is overly simplistic and inefficient, binary search improves row processing but misses inter-row relationships, and the top right corner approach strikes the perfect balance between logic and performance. By thoroughly analyzing the problem constraints and utilizing the sorted structure of the matrix, the top right corner approach clearly stands out as the optimal solution. Its linear complexity of O(m plus n) ensures it performs well for both small and large matrices. Additionally, its single-pass nature minimizes unnecessary computations, making it both time-efficient and intuitive once the movement logic is understood. This approach is not only practical but also elegant, demonstrating the power of leveraging problem constraints for efficient problem-solving. Here, we are tasked with finding the leftmost column in a binary matrix that contains at least one 1. The matrix has a key property: each row is sorted in non-decreasing order, meaning all the zeros in a row appear before any 1s. Our goal is to identify the smallest column index, starting from 0, that contains a 1. If there are no 1s in the entire matrix, we return -1. To begin solving this, we can use a brute force approach. The intuition behind this method is to leverage the sorted rows. By iterating through each row, we can perform a linear search to find the first 1. Once we find a 1, we can stop searching further in that row, as all subsequent columns will also contain 1s. The leftmost 1 across all rows will give us the result. Let's break this approach into detailed steps. First, we initialize a variable min_call to infinity to track the smallest column index where a 1 is found. Then, for each row in the matrix, we perform a linear search. If a 1 is encountered, we update min_call and break out of the loop for that row. Finally, after checking all rows, if no 1 is found, we return -1. Otherwise, we return the value of min_call as our result. Now, let's look at the pseudocode for the brute force approach. We start by initializing min_call to infinity. Then, for each row in the matrix, we iterate through its columns. If we find a 1, we update min_call to the smaller of its current value or the column index of the 1. After that, we break out of the loop for that row, as all subsequent columns will also contain 1s due to the sorted nature of the row. At the end, if min_call is still infinity, it means no 1 was found in the entire matrix, so we return -1. Otherwise, we return min_call. The key insights here are that the sorting property of the rows allows us to stop the search early once we encounter a 1, and we use a global variable min_call to track the leftmost column containing a 1. This approach is simple to implement and works well for smaller matrices. Additionally, there are some important edge cases to consider. If no row contains a 1, the algorithm correctly returns -1. Similarly, if all rows are filled with only zeros, the early stopping mechanism ensures we don't perform unnecessary checks. For data structures, the binary matrix is represented as a 2D list where each row contains sorted binary values of zeros and ones. The variable min_call is used to keep track of the smallest column index with a 1. Now, let's analyze the complexity of this brute force approach. The time complexity is O, n*m, where n is the number of rows and m is the number of columns, as we might potentially iterate through every element in the matrix. The space complexity is O(1), because no additional data structures are used. To optimize this further, we can use binary search. The intuition here is that since the rows are sorted, we don't need to perform a linear search. Instead, we can use binary search to find the first occurrence of 1, reducing the search time for each row. Let's break down the optimized approach using binary search. First, we initialize min_call to infinity, just like in the brute force approach. For each row in the matrix, we perform a binary search to locate the first one. If we find a 1, we update min_call to the smaller of its current value or the column index of the 1. The binary search works by dividing the row into halves. If the middle element is 1, we update min_call and continue searching the left half of the row to find an even smaller column index. If the middle element is 0, we search the right half of the row. This process continues until we either find the first one or exhaust the search space for that row. After checking all rows, if min_call remains infinity, it means no one was found, so we return -1. Otherwise, we return min_call. The pseudocode illustrates this process clearly. By replacing the linear search with binary search, we significantly improve the efficiency of the algorithm. Finally, let's analyze the complexity of the binary search approach. The time complexity is O, n*log_m, where n is the number of rows and m is the number of columns. The binary search reduces the search time for each row from O(m) to O(log_m), making this approach much faster for matrices with a large number of columns. The space complexity remains O(1), because no additional data structures are used. The key insights here are that binary search efficiently exploits the sorted nature of the rows, allowing us to minimize the number of elements we need to check. Additionally, we can stop searching further columns in a row as soon as we find a 1, saving even more time. Compared to the brute force approach, binary search is far more efficient for large matrices, although the brute force method is simpler to implement and works well for smaller matrices. Ultimately, the binary search approach is recommended for scenarios where performance is critical, while the brute force approach can be a good choice when simplicity is prioritized. This Python implementation solves LeetCode problem number 1428, leftmost column with at least a 1. The problem requires finding the smallest column index in a binary matrix that contains at least one 1. The matrix is sorted such that all zeros appear before ones in each row. The solution uses the binary matrix API provided in the problem. The dimensions of the matrix are retrieved first, allowing us to determine the number of rows and columns. We start at the top right corner of the matrix, which is the last column of the first row. This position is ideal because it enables efficient navigation of the matrix. The algorithm maintains two pointers, row and call. While row is within the bounds of the matrix, less than the total number of rows, and call is non-negative, greater than or equal to 0, the following traversal is performed. 1. If the current cell contains a 1, we update leftmost to the current column index, call, and move left by decrementing call. This step ensures that we continue searching for an even smaller column index that might contain a 1. 2. If the current cell contains a 0, we move down to the next row by incrementing row. This step is based on the sorted property of the matrix. If the current column contains a 0, it cannot contain any ones above it. The traversal stops when we either move out of bounds, row exceeds the number of rows, or column index becomes negative. If no one is found in the matrix, the function returns -1. Otherwise, it returns the leftmost column index identified during the traversal. This approach has a time complexity of O, rows plus calls, as we either move left or down in each step, ensuring linear traversal of the matrix dimensions. The space complexity is O(1), since no additional storage is used beyond a few variables for matrix traversal. Here, we begin our Java implementation for the problem leftmost column with at least a 1 using the binary matrix API provided by LeetCode. First, we define the binary matrix interface, which includes the methods get for accessing specific elements in the matrix and dimensions for retrieving the matrix's number of rows and columns. In the solution class, we implement the method leftmost column with 1. The first step is to retrieve the dimensions of the matrix using the dimensions method and store the number of rows and columns in variables rows and cols. Next, we initialize our starting position at the top right corner of the matrix, setting row to 0 and col to cols 1. Additionally, we declare a variable leftmost and initialize it to -1, which will serve as our default return value if no column contains a 1. Finally, we begin traversing the matrix with a while loop that continues as long as our position is within the matrix bounds, specifically while the row index is less than the total number of rows and the column index is greater than or equal to 0. Inside the traversal loop, we check the value of the current cell at the position defined by row and col. If the value is 1, it means we have found a potential leftmost column containing a 1. In this case, we update the leftmost variable to the current column index and move one step to the left by decrementing col. If the value is not 1, we move down to the next row by incrementing row. This approach ensures that we explore all potential positions efficiently without revisiting any cells. Once the loop completes, we return the value of leftmost, which either holds the index of the leftmost column with at least 1 or remains -1 if no such column exists. This completes the implementation of our solution. The problem we're solving is to find the leftmost column in a binary matrix that contains at least 1. The matrix is sorted in non-decreasing order for both rows and columns. If no column has a 1, we return -1. To solve this, we use the binary matrix API, which provides two key methods, get, row, col, to access specific elements, and dimensions, to retrieve the matrix's size. For example, consider a 3x4 matrix where each row is sorted. We start at the top right corner, which is position 0, 3, and initialize our variables. This approach allows us to systematically navigate the matrix to find the solution efficiently. We also initialize leftmost to -1 to keep track of the leftmost column containing a 1. In the first iteration, we check the value at 0, 3 using binary matrix.get 0, 3 and find a 1. This means column 3 is a candidate, so we update leftmost to 3 and move left to column 2. In the second iteration, we check the value at 0, 2 and find a 0. Since it's a 0, we move down to row 1, staying in column 2. In the third iteration, we check 1, 2 and find a 1. This updates leftmost to 2, and we move further left to column 1. In the fourth iteration, we check 1, 1 and find a 0. Again, we move down, this time to row 2, staying in column 1. In the fifth iteration, we check 2, 1 and find a 1. This updates leftmost to 1, and we move left to column 0. Finally, in the sixth iteration, we check 2, 0 and find a 0. Since we've reached the last column, we move down, which exceeds the number of rows. The process stops here, and the result is the value of leftmost, which is 1. This means column 1 is the leftmost column containing at least 1. In contrast, if the matrix contains no 1s, the result remains -1. Let's look at an example where no 1s are present in the matrix. For a 3x3 matrix where all elements are 0, we initialize the same variables, rows equals 3, cols equals 3, starting at 0, 2, with leftmost equals -1. In the first iteration, we check 0, 2, and find a 0, so we move down to row 1, staying in column 2. In the second iteration, we check 1, 2, and again find a 0, so we move down to row 2, still in column 2. In the third iteration, we check 2, 2, and find a 0 once more. Moving down now exceeds the number of rows, and since no 1s were found during the process, the result remains -1. Now, let's consider a simpler case with a single row matrix. In a single row matrix with dimensions 1x4, we again initialize rows equals 1, cols equals 4, starting at 0, 3, with leftmost equals -1. In the first iteration, we check 0, 3, and find a 1. This updates leftmost to 3, and we move left to column 2. In the second iteration, we check 0, 2, and find another 1. Now, leftmost is updated to 2, and we move left to column 1. In the third iteration, we check 0, 1, and find a 0. Since there's only one row, moving down exceeds the number of rows, and the process stops. Here, the result is leftmost equals 2, meaning column 2 is the leftmost column containing a 1. The key insight of this solution lies in starting from the top right corner of the matrix. By moving left when encountering a 1 and down when encountering a 0, we minimize the number of checks needed. This approach ensures that we only traverse each row or column once, leading to a time complexity of O rows plus calls. This makes the solution highly efficient for large matrices while maintaining clarity and simplicity in its implementation. The time complexity of the solution is O rows plus calls, where rows represent the number of rows in the binary matrix and calls represent the number of columns. This is because the algorithm starts at the top right corner of the matrix and makes a decision at each step to either move left, reducing the column index, or move down, increasing the row index. In the worst case, the algorithm will make one move for each row or column. For example, moving left decreases the number of columns remaining to process, while moving down reduces the number of rows left to check. This ensures that the total number of moves is bounded by the sum of rows and columns. In the best-case scenario, if a 1 is found in the first column, the algorithm terminates early, resulting in a time complexity of O min rows calls. On average, the algorithm traverses a combination of rows and columns and still operates within O rows plus calls. In the worst case, such as when there are no ones or the leftmost one is in the bottom left corner, the algorithm explores all rows and columns, confirming the time complexity is O rows plus calls. To further understand why the time complexity is O rows plus calls, consider this mathematical proof. Assume the number of rows is n and the number of columns is m. In the worst case, the algorithm first moves left m times, traversing all columns until the column index becomes -1, and then moves down n times, reaching the last row. Combining these moves gives a total of m plus n, which simplifies to O rows plus calls. Moving on to space complexity, the solution operates with a constant space complexity of O1. This is because it only uses a few integer variables, specifically row, call, and leftmost, to track the current state. No additional data structures or recursive calls are necessary. Even though the matrix is accessed through the binary matrix API, which provides methods like dimensions and get, these accesses do not contribute to the auxiliary space usage. The memory overhead remains fixed, regardless of the size of the input matrix. To contrast the efficiency of the current approach, let's compare it to the naive solution. The naive method involves scanning the entire matrix row by row, finding the leftmost one in each row, and tracking the minimum column index across all rows. This approach results in a time complexity of O rows asterisk calls, because every element in the matrix is visited individually. In comparison, the optimized solution leverages the sorted property of the binary matrix, which ensures that rows are in non-decreasing order. By starting at the top right corner and eliminating rows or columns at each step, the algorithm avoids unnecessary checks and achieves a time complexity of O rows plus calls. In terms of space, both approaches use O1 space, as no extra memory is allocated beyond a few variables. Overall, the optimized solution is far more efficient for large matrices, as its linear time complexity scales much better than the quadratic time complexity of the naive approach, making it ideal for handling large datasets. When solving this problem, there are several common mistakes to watch out for. First, many beginners overlook the fact that each row in the matrix is sorted. Treating the matrix as unsorted can lead to brute force solutions that have a time complexity of O m n, which is far from optimal. Another mistake is using binary search on every row. While this reduces the search time for a single row to O log n, doing so for all rows still results in O m log n complexity, which is less efficient than other approaches. Additionally, some programmers misinterpret the problem constraints, assuming a global order or diagonal relationships between elements. This misunderstanding can lead to flawed logic. Edge cases are another common pitfall. For example, matrices with number ones, matrices filled entirely with zeros or ones, or those with just a single row or column often cause errors if not handled properly. Lastly, inefficiencies can arise if the same column is searched repeatedly in certain approaches, leading to redundant computations and unnecessary increases in runtime. Now, let's focus on insights that are particularly relevant for interviews. Recognizing the key pattern in this problem is critical. Both rows and columns are sorted, which suggests specific techniques like binary search, pointer-based methods, or optimized matrix traversal. Interviewers often assess your ability to identify this pattern quickly. Another important point to discuss is the trade-off between time complexities. While binary search on rows offers an O(m*log n) solution, an optimized traversal approach achieves O(m plus n), which is better. Being able to articulate why one approach is more efficient is a skill that interviewers value. Don't forget to explicitly discuss edge cases during the interview. For instance, be prepared to explain how you'd handle empty matrices, matrices with number ones, or those with only one row or column. Finally, practice explaining optimal traversal strategies, such as starting from the top right or bottom left corner. This approach works well because the sorted structure of rows and columns allows you to eliminate parts of the matrix as you traverse. There are also related problems and alternative approaches to consider. For instance, LeetCode 74, Search a 2D Matrix, and LeetCode 240, Search a 2D Matrix 2, involve similar traversal techniques for sorted matrices. LeetCode 378, KTH smallest element in a sorted matrix, adds a different twist by combining sorting with heap-based strategies. And, of course, LeetCode 1428 itself is a great example to practice this exact skill. As for approaches, the brute force method involves checking every element in the matrix. While simple, it's inefficient with a time complexity of O(m*n). Using binary search on each row is faster, with O(m*log n), but still not optimal. The most efficient solution is an optimized traversal, starting from the top right or bottom left corner, which leverages the sorted properties to achieve O(m plus n). There's also the divide and conquer approach, where the matrix is split into quadrants and searched recursively. While this method is elegant, it's often more complex to implement and typically slower than optimized traversal in practice. That's it for today's session. We reviewed a problem-solving approach to efficiently find the leftmost column with a 1 in a binary matrix, leveraging its sorted structure. Remember to practice similar problems to strengthen your skills. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!